This seems like we're getting close to the end of the semester with radio chemistry, nuclear chemistry, and such. But interestingly, the kinetics, the rate at which radio decay happens, very, very similar to, mathematically similar to the kinetics of first order chemical equations as well. Which, if you remember or not, here are the equations that govern first order chemical changes, and also where it also applies to medicines in the body often decay or metabolized in first order time dependence. Anyways, the rate of a reaction, so the rate of the chemical decay, the rate of the nuclear decay equal to some nuclear decay constant K times the number of particles. And if we integrate that, both sides, over time, we find this. And the way to rearrange that is like this, often like this. NO is the original amount, and N is the amount of the stuff at time t. And another important term, which we'll often hear about, is the half-life. The half-life of decay is the time it takes for a half of that substance to decay away into something else, and that's 0.693, the constant. I think it's the natural log of a half, I think. And the little k is the same as little k here. So if we know the half-life, we know the constant, or if we know the constant, we know the half-life, and that can get us quite a ways. Alright, so example number 1. Americium is a radioactive sample used in smoke detectors of all things. If we start with 5 grams and it has a half-life of 433 years, let's fiddle with that a little bit and just see where we get. For example, the half-life is 433 years, so the constant K for that decay is 0.0016 years to the negative 1. So what? What does that mean? Well, let's say I had 5 grams, like I said a second ago, of that americium. That comes down to a whole bunch of atoms, what, about 1/10 of a mole or so? No, it's got to be less than that. I'm going to want to check that math, but in any case, looks like, hang on a second, let me just check that. Alright, yeah, that's right. So in any case, it's a lot of atoms. A lot of particles, and we're saying the rate of the decay then depends on that number of particles. So take that number of particles and multiply it times the rate constant, the decay constant, and voila, I have a large number of decays per year. Or if I want to change that decays per year into decays per second, you know how to do that. Well, maybe you don't, maybe you've forgotten. It's just a simple conversion from years to seconds. But to make the years cancel, the days cancel, the hours cancel into seconds. That's how I set it up. Interesting. Now, often, no one's going to really hook up, well, you could hook a Geiger counter or a scintillation counter up to a computer detector and have it count for you the number of decays per second or the number of decays per few minutes. And so in a sense, I suppose that's a realistic question. But let's say we start at the 5 grams of americium again, and its half-life was 433 years, and I found this constant from that. 5 grams can go here. Oh yeah, that's a slightly different way to use the first order equation, but it still works. And 10 years, and 10 years times 0.0016, 1 over years, and the natural log of 5, and we do the math. Oh yeah, to get rid of the natural log, it's e to the x. And it looks like after 10 years, the 5 grams would have gone down to only 4.92 grams. There would be 0.08 grams of something lingering around, probably whatever the decay product of americium would be. I'd have to go back and look it up, figure out what kind of a particle it gives off when it decays. Example number 2, copper 64. Half-life of 12.8 days. Maybe I might want to know that in seconds, so I changed it. That's, goodness gracious, that's 1,000,000 and something seconds. But the constant then is a millionth-ish on the order, and it's seconds to the negative 1. Or I could have left it in days and gotten my half-life in, or my constant in units of 1 over days. But let's say I had 30 milligrams of copper 64 freshly produced, and I might change milligram. Oh, darn it, I made a little boo-boo. Alright, sorry about that pause. Yeah, I saw I made a mistake. 30 milligrams is 0.03 grams. Grams to moles, moles to particles, and voila, 2.82 times 10 to the 20th nucleuses of copper 64. Therefore, if my constant is as above, and I have that number of particles, I would imagine to see this large number of decays every second, and that's unimaginable. I can't imagine that many decays every second. But, story. How long for this isotope, how many seconds, hours, days, years, for it to decay to 25% of its original value? This one's pretty easy to, well, the easiest way is to use the equation in this form. When N0, the original amount, decays to 25%, my new amount is 25% of the old amount, or the original amount. So basically this is 0.25 as a percent as a decimal, and this is the constant, and I'm curious about the time. And just solve for the time. Let's see, did I do this? Yeah, the natural log of 0.25 is negative 1.386, and take this constant, divide it over into that, and answers 2,210-ish seconds. I suppose that's why you would need to make the new copper 64 fresh before it started to decay away if you wanted to use it for something. Radiodecay, yeah, oh yeah, carbon 14. Last topic, last example, just about my last example. So carbon 14 dating, I'm sure you've heard of it, or I don't know where you've been, but they use this to estimate the age of an old living thing, once living thing. As the organism decays and dies and decays, the carbon-14 begins to radioactively decay into nitrogen, I believe, nuclei. But in any case, the half-life is this, and therefore the constant is this. So if I had an estimate of the amount of decay in living matter, 13.6 counts per minute per gram, then I measure how many counts per minute per gram that I measure occurring in my object in question, trying to find out how old it would be. Really, all you do is you take that ratio of 1.2 to 13.6 in this equation, the current amount versus the original amount, which is a pretty good estimate. The constant is this, as figured from above, and lo and behold, this object, I think it was a tree in my silly story from above, is 20,000 years old. Oh, dang, I have one more example. Let me scurry through this one as well. Like I said earlier, medication. Let's say medicine's administered, 10 milligrams of medicine's administered. The half-life is 1.75 hours. That means after 1 3/4 hours, half of that medicine has been biodegraded or metabolized into something different. How much of the 10 milligrams will be left after 4 hours? Well, this should look very familiar. I did my constant in one swoop here with the T1 half-life divided into the 0.693 after 4 hours. How much will be left of 10 milligrams? Don't forget to get rid of the natural logarithm. It's e to the x on both sides. And looks like only 2 milligrams will be left after 4 hours, 2.05. Wow. Alright, thanks guys. That's again first order decay of many processes. Thanks. See you in class. Have a good one.